let me start off by giving you first a little bit of a high-level view of what I mean by cryptographic leash. So if you think of a quantum computer, well, first we have, in order for it to work well, we need for it to be coherent, so we cannot really look inside and see what it's doing. And then secondly, it's also exponentially powerful. That's the whole point of using a quantum computer. So if you look at it from our viewpoint as a classical verifier, then keeping tabs on the quantum computer is a little bit daunting. So a cryptographic leash sort of takes this black box, and the whole point is it makes it a little bit takes this quantum computer and makes it sort of tries to level the playing field by using cryptography. Now, in the process, we get a number of protocols for scalable proofs of quantumness, certifiable randomness, also for testing quantum memory and for classically verifying quantum computation and delegating into the cloud. Okay, so just as a backdrop, let me remind you all. You all know about the quantum supremacy experiment from Google and others. So in that case, the verification took exponential time, so it does not scale. But there's another aspect of it, which is that it used this problem of random circuit sampling, which was really a very nice idea, but it sort of represented circuits which a machine that was sufficiently noisy that really all you could do was run this random circuit and sample an output with some fidelity. Okay, so one of the things that's happened since is that there have been spoofing attacks on all these different supremacy experiments, both classical spoofing attacks as well as attacks on the underlying justifications saying that these are classically hard problems. So what would we like to do in the future to follow up on these kinds of experiments? So one thing we could try to do is come up with scalable proofs of quantumness. So what this means is that we want the classical verification to be efficient, meaning polynomial time computable. And we can also see this as a goal, that one of the goals is to provide an intermediate scale milestone towards fully scalable quantum computation. Meaning we want to come up with a simple quantum computation beyond random circuit sampling that provides some kind of a proof of quantumness, that shows that the quantum computer was doing something that was really hard to do classically. Now, and then once we succeed in doing this and building up a primitive, then we'll actually open the way to other tasks as well that I've described. So one of the things that we'd be doing in this process is allowing the classical verifier to reach into Hilbert space. And the way the classical verifier reaches into Hilbert space is by coming up with a convincing proof that the quantum computer actually created a qubit in a particular state, in a state that the classical verifier knows, and that having created this qubit, the untrusted quantum computer will act on it on command. So this is the sense in which the classical verifier gains control over the quantum computer. And to do this, we need this cryptographic leash. So actually, you should think of this as using post-quantum cryptography. Although we might relax that assumption a little bit later for certain applications. Okay, so post-quantum cryptography, of course, we know that quantum computers aren't all-powerful, that they are classical crypto systems that even quantum computers cannot break. So these are crypto systems where you can encrypt classically, and if you have a secret key or the trapdoor, then you can decrypt messages efficiently. But on the other hand, if the quantum computer does not have this secret key, then it then it cannot decrypt efficiently. So, okay, so now let me describe to you very, very briefly what kind of a cryptographic primitive we need for what we'll do. So what we're going to use is something called a trapdoor claw-free function. So this is a kind of crypto system where your encryption function is 2 to 1. So for any message, there's a second one that maps to exactly the same encryption value. So and these three strings x0, x1, and y will be called a claw. So this function f has the property that you can efficiently compute it. Anybody can efficiently compute it. It's without the secret key, it's hard to find any claw, any x0, x1, and y. But with the knowledge of the secret key or trapdoor, you can invert any given y to find x0 and x1. So you can find claws. Okay, so you can implement trapdoor claw-free functions based on classical cryptography, and in particular, you can base them on LWE, learning with errors, which is one of the prime candidates for post-quantum crypto. So this is just LWE just says if you're given a bunch of noisy equations mod q for some modulus q. But now, they are noisy equations. So you are given, if there are n variables, you're given many more than n equations, so that the solution S is uniquely defined given y. But then, even though it's uniquely defined, it's very hard to find the solution. So that's the hard function. So now, based on this, we can set up this what's called this very simple protocol called the qubit certification protocol, which implements this functionality that I described earlier, which is that the quantum computer ends up with a qubit, which is actually a random qubit, where it's either in the plus state or the minus state, depending upon this bit b. Which is going to be uniformly random. So the state psi is going to be, without knowledge of b, it's a uniform mixture of plus and minus, so it's a totally uniform qubit. But now the quantum computer only knows an encryption of b. So the quantum computer doesn't know what this qubit is, but the quantum computer can send the encryption of b to the verifier, who can use knowledge of the secret key to figure out what b is. So now you have this interesting situation where the classical verifier can force the quantum computer to create a certain qubit and manipulate it, but the quantum computer doesn't know what the qubit is, and so is unable to tamper with it. Okay, so once you have this functionality, you can do a lot of things with it. So let me show you what. Give you a sense of what the protocol to do this looks like. So the protocol is quite simple. So what the verifier does is sends a description of this 2 to 1 the claw-free function to the quantum computer. So this might just mean the LWE sample. The quantum computer does a measurement, sends back y, which is going to be, remember, it's the output of the function. Now the classical computer sends back a challenge, 0 or 1, saying either give me back a pre-image of y, or give me back d, which is another n-bit string, which is some sort of an equation linking x0 and x1, the two pre-images. Okay, so now here are a couple of facts. One, the quantum computer can efficiently run through this protocol. So the quantum computer can go through it, and regardless of which challenge the verifier asks for, it can provide the correct answer to it. That will satisfy the verifier. On the other hand, no polynomial time classical or quantum computer can answer both challenges, both pre-image and equation. So I claim that this second condition, which is symmetric in quantum and classical, actually implies that no classical computer can succeed in this protocol, except with probability about a half. And the reason is that a classical computer can be rewound. So you can sort of start the computation off and start the protocol off and provide the challenge 0, so you get a pre-image. And then what you do is you rewind the state of the classical computer to what it was right after it committed to Y, and then give it the other challenge. And so since a classical computer has state and it can be rewound, if it's willing to answer either challenge, it must be willing to answer both. And so that contradicts this cryptographic condition. So here's the underlying quantum computation that the quantum computer must perform. And this is, as you'll see, the most basic of quantum computations. So what it does is it goes into a superposition over all x, by say starting with 0 and doing a Hadamard transform, and then it computes f of x in superposition. Now that's the major computation it does, and then it measures f of x to get y, which it sends back, and it's left with the first register in superposition, consistent with y, and then it's based on the challenge, it measures that first register. So that's the entire protocol. So again, basically, in this particular case of a 2-to-1 function, once it does the measurement, it gets a random y in the image, and then it has the first register is in a superposition of the two pre-images, which you can measure in the standard basis to get one of the two pre-images with probability half each. But then if you measure it in the Fourier basis, the Hadamard basis, then you get a random string D such that D inner product with x0 plus x1, so this is bitwise sum mod 2, so that inner product is 0. And so this is something that this is an equation that the verifier can check, because given y, the verifier knows what x0 and x1 are. Okay, so okay, so I think I should skip this, but basically what I should say is out here, the verifier, we said if a classical computer did this, it can answer both questions, which means the verifier is getting back one of the pre-images and is getting back one bit about the two pre-images, one joint bit, what this inner product of these two is. And so it turns out that we need a stronger property which says that no classical computer could possibly answer both questions, for a y of its choice. And this is what we call a hardcore bit. It's called an adaptive hardcore bit. And so one can show that for the particular kinds of trapdoor or claw-free functions we are looking at, this adaptive hardcore bit can also be proved to be as hard as finding a claw, and therefore it's cryptographically hard. Okay, so what this means is that if a quantum computer carries out this protocol successfully, then it's done something that no classical computer could do without breaking the crypto system, meaning without taking exponential time. Okay, so in that sense, it gives you a proof of quantumness. So now, once we have this primitive, we can do more with it. So it turns out that what I said with a little bit of work is already enough to generate certifiably random numbers. So what's the certifiably random numbers? What we want is an untrusted box, which we want to input a small number of truly random bits, and we want as output a much larger number of statistically random bits, not pseudo-random, but statistically random. And so what we can what we can do with this protocol is we can achieve this, and the certification lies in certifying that this particular output string must be random. Okay, and this is something that you can't possibly do classically. So again, the reason one can do this quantumly is because you can reach into the quantum computer's Hilbert space and show that if the verification succeeds, then it must have created a qubit, which by rotation we can think of as in the state 0, and that it measures in the standard basis on challenge 1 and in the Hadamard basis on challenge 0. And the way we are reaching into the Hilbert space and characterizing this qubit is, it's sort of this is the interesting part that you can, by these classical tests, you can actually reach in and say the internal state of this completely untrusted quantum computer must be something. Okay, so let me just move on and say, what else can you do with this simple protocol? So you can now start modifying this basic protocol in a number of ways. Using, for example, you can say, well, the quantum computer cannot distinguish whether we are giving it a 2-to-1 function or a 1-to-1 function or many-to-1 function, for example. Or there are other modifications we can do. So here's a first modification, which is we can actually do the proof of quantumness without this adaptive hardcore bit, which was one of the constraints we had on the classical cryptography we could use, the post-quantum cryptography we could use. So what we use instead is a random oracle. Okay, a random oracle meaning there's, on input any n-bit string, it gives you back a random bit, a particular random bit. So this is, this is a model which is, you could think of it as achieved in real life by a cryptographic hash function. But for the purposes of proof, we sort of model it by a random oracle and show. Okay. So now what you do in the modification you make to the protocol is now when the quantum computer, after it commits to Y, when it's left with a superposition of 2 n-bit strings x0 and x1, then what the quantum computer does is it also then computes this cryptographic hash function. So it computes this single bit, this random looking bit, h of x0 or h of x1. And then there's no interaction. There's no further interaction. So there's no challenge. All it does is it measures all these n+1 bits in the Hadamard basis and returns them. So this removes the need for interaction. It also removes the need for a adaptive hardcore bit, and so you can do a more efficient implementation based on ring LWE. Okay. Oops. So there's another way you can do a proof of quantumness without an adaptive hardcore bit, where you can modify the basic protocol to incorporate a Bell type, CHSH game. Okay, and so in these Bell experiments, you need spatially separated players. And so these are simulated, the fact that these are spatially separated is simulated by this computational hardness of the crypto problem, which says 2 parts of the quantum computer really have no idea what each of them are doing. Essentially, they're spatially separated. And again, now you can use a simpler x² mod n as a trapdoor claw-free function, which is not even post-quantum secure. So there was a small-scale proof of concept implementation of both the original unmodified scheme as well as this particular proof, this particular scheme on an ion trap quantum computer, where the experimental challenge was implementing intermediate measurements. We didn't actually do the previous scheme in there. Now, there are other modifications you can make. So there's a variant on this qubit certification protocol where you can generate n bits of randomness using just the simple one, the basic protocol with a small variation, just once. So in the process, you can also test that the quantum computer has n qubits of memory. So again, this is done by providing the quantum computer with either a 2 to 1 function or a 2 to the k2 function, and it doesn't know which one it is, and that sort of allows one to generate lots of random bits in one shot. Now, I'm sure you've heard of Urmila Mahadev's work on delegating quantum computation to the cloud while maintaining privacy of the data, or verifying the correctness of output of a quantum computer, and that also builds on this basic protocol. So I should be wrapping up. So I won't say how this is done, but I'll just sort of wrap up by summarizing. So what I was describing was that there's a way you can implement a cryptographic leash, a way that a classical verifier can use cryptography to keep a quantum computer honest. Okay, so here's one way you can think about it. There's sort of how you can there's all the work people do as experimentalists or designing the hardware, where they're trying to make sure that the computer is reliable. And then there's error correction, which ends up saying, look, let's put in checks in there in the software so that our errors, which are localized, don't get to see some of the checks, and these checks can be used to make sure that the computer is actually doing the right thing. So you can think of the cryptographic leash as bumping this up one level in the software, where we are now putting in other kinds of checks, which are being done by the classical controller of these qubits, and you end up through this cryptographic leash making sure that the hardware is reliable. Now, another way to think about these protocols is that their goal is to create an intermediate scale milestone for quantum computers, meaning, moving on from this very short term where the error rates are so high that you really can only implement random quantum circuits and just see whatever they throw out. If you have enough qubits and enough fidelity so that you can now carry out a somewhat larger computation, but somewhat reliably, then what can you do with it? And the hope is that these kinds of cryptographically leash-based protocols would provide this next level of things that you can do. So there's active research going on given all these different styles of protocols, can we put them together to come up with the minimum possible resources we need for number of qubits, number of gates, for proofs of quantumness and certified randomness. And of course, there are many theoretical applications of these ideas. Okay, thank you. I'll stop here.